This study is aimed to find an answer if it is possible to make a medical device which is cheap and trustable to predict lung diseases. The proposed device operation is based on deep learning model which can work in a microcontroller. In deep learning part, I select CNN as a deep learning model and trained its own lung set with the addition of COPD recordings. Since I don't have sufficient data to train the deep learning model, I use data augmentation. When I choose the data augmentation method, I consider to preserve the frequency characteristic of the lung sound. The new data should be different characteristic and they should be carry sufficient information about the lung diseases. So the selected data augmentation methods are time shifting and segmentation. Time shifting is basically shifting the digital signal in time domain. Here is the figure of the original and time-shifted samples. Upper side belongs to the original sample and downside belongs to the shifted sample. As you can detect from the shifted sample, there is a noise below the 64 Hz. With the time shifting, overall information is conserved, but the patterns are changed. Thus, the deep learning model will extract new features. Only use mass spectrogram images to fed convolutional neural network. To see how time shifting and segmentation will affect the training, I use mean square error method to find difference between original and new data. Mean square error calculates the difference of 2 pixels at the same location then make arithmetic calculation. The figure at downside has results of different data as when we compare them with the results at the upper figure, they can be considered as a new data. I use fourth order Butterworth bandpass filter which filters from 100 Hz to 1000 Hz. If you remember from the time shifting process, there was a noise when the time shifting process occurred. To avoid from the noise, I filtered the sample after time shifting process. Butterworth filter does not delete any information from the sample. It basically changes the amplitude of the signal. To determine the segment's duration, I made an analysis on dataset which contains 40,000 inhalation and exhalation cycles. According to this analysis, there is a 2 cycle of inhalation and exhalation in 5 seconds. Frequency characteristic is preserved. The new segments carry sufficient information. Here is the segment difference values based on mean square error methods. At the beginning, I have 20 COPD and I had 35 healthy and 33 asthma recordings. After the data augmentations, I had 839 data from these original samples. Convolutional neural network extracts meaningful information by convolution process. It is highly effective in image processing and object recognition, but it is also effective in time series applications. At the beginning of the presentation, I mentioned about a deep learning model which can work in a microcontroller. At the first step, CNN must be fit into the microcontroller. This development board has 2 megabytes of flash memory and 256 kilobytes of RAM. So the model must be less than 2 megabytes and it must require less than 256 kilobytes of RAM. I had 839 data after data augmentation. This amount of data is still insufficient to train a deep learning. To avoid this problem, I use transfer learning, and the selected transfer learning model is MobileNet V3. It stands out from other popular transfer learning models as it is becoming efficient and lightweight. It's achieved to lightweight with the use of depth-wise separable convolution layers. Only the small minimalistic architecture is fit into the microcontroller, and when I built the MobileNet V3 model, I had 2 options. Whether I can use global pooling layer or I can build a model without global pooling layer. I tried 3 of them and I get the best results without global pooling layer. It means that global pooling layers are decreasing the lung sound related information. The simulation results were not trustable when we think it will predict the health condition. It was due to there was insufficient amount of data. But the results were promising. With the sufficient data, a deep learning model can be embedded into a microcontroller. So it is possible to make a medical device that needs low power while working and does not require internet connection to work on and cheap.